Hey there, good morning guys. We are going to look at lesson 3, simple machines, and we are just going to look at my book. You don't really want to look at me right now. I am not looking so hot, but I wanted to get through some of this with you guys. So we're going to look at what is highlighted. Before we do that, I want to show you what your assignment is going to be. It's going to be on Google Classroom, and it's going to be this document, okay? It's going to be your lesson 3, and you're going to be filling out a note page on the computer about this. So you're going to be answering this question: what is simple machine? And then define and explain the following terms and how they're related to simple machines. I put a little note here. You're going to need to kind of keep flipping back to lesson 2 because this assignment kind of overlaps between lesson 2 and lesson 3. So you're going to define and explain how these are related to simple machines: mechanical advantage, input force, output force, which, by the way, output force is the same thing as output work, okay? Distance and size and direction, so how these things relate to forces. And if you remember from lesson 2, distance, size, and direction, this is what you're going to want to keep flipping back to, okay? Distance, direction, okay? Increase force, okay? This section here is really going to be helpful to keep flipping back to as you're talking. And remember this here too, this is really key also, that no matter what type of machine is used, the output work is never greater than the input work. It's always the same, okay? A machine makes work easier, okay, by changing the amount of force you need, the distance, or the direction, but it does not change the total amount of input work and output work. It stays the same. That's a really key point. And like I said, these ideas right here, these pictures from lesson 2 are going to be really important to keep looking at when you do this assignment. Okay, some of it's going to be from lesson 2. Okay, and then the second part of that assignment is going to be this chart, okay, that you're going to fill out on Google. We're listing the type of machine, an explanation, and examples. So the explanation, be sure to include why it's considered a machine. I put a little note here, make sure you're looking back at lesson 2. Again, this is going to kind of overlap. Your explanations must be clear, easy to understand. The terms mechanical advantage, input, output force, distance, size, and direction are used when possible and appropriate. Okay, and I'm going to do one example with you. We're going to do inclined plane together. So you get an idea of how this is going to look, this chart. And then 3 examples and a small picture. Okay, I know you're good with that part. You might have to do some Googling. They don't always give you enough examples in the textbook, but that's fine. Okay, so let's go back to the book here. I know, this was as good as I could get my camera angle. So my book, remember, looks a little different than yours because this is the teacher version. So there's really nothing I would need you to do except follow along. You can jot some notes if you want on your own. You might need to go back and look at this video later, okay, but I wanted you to do it as a class first. So of course, our definition of simple machine, okay, does work with only one movement. A compound machine is a combination of simple machines. They give you some examples: a can opener, a bicycle. Okay, so then they go through and talk about the 6 simple machines, which are also listed in this assignment. Okay, and you do have to have all 6 in your Rube Goldberg. So this is where this is all starting to tie together. Okay, all right, so inclined plane, here's your definition. This is the key here for inclined planes. As the inclined plane becomes longer, the force needed to move the object becomes smaller. Okay, that's so the longer the inclined plane, the less input force you're going to need. And this example right here on this page is fantastic. Okay, right here. This box, okay, if I just lifted it from the ground, that would be a distance of 1 meter, and I would need to use 1,500 newtons of work. Remember that definition of work, that formula was work is force times distance, okay? So 1 times 1,500 is 1,500. I would need to do 1,500 joules of work, which is what it talks about here in the text, okay? Now, let's use an inclined plane. Now my distance is 5 meters, and the force I need is 300 newtons. So I'm still doing 1,500 joules of work, but I'm only using 300 newtons of force, okay, instead of 1,500 newtons of force. So again, the total amount of work done doesn't change. It's 1,500 joules, but it's easier for me to do. It feels easier because I'm only using 300 newtons of work instead of 1,500 newtons of work, okay, of force. So that's a really good example, and it tells you right here about the mechanical advantage of an inclined plane is the length of the inclined plane divided by its height. Remember, we talked about mechanical advantage back here in lesson 2. Okay? How much larger the output force is compared to the input force. Okay, is the mechanical advantage right there. Okay, from lesson 2. All right. Okay, so let's look back at this chart that you're going to be doing for homework. I can't fit it all in there. When you do this on Google Docs, this will automatically get bigger as you type, but I don't have that, so I wanted to show this. So I wrote out my own, and I know my handwriting's messy. Just help each other. Pause the video. I did my best. Okay, so here's my inclined plane. Here's my explanation. I highlighted the keywords that it said it wanted me to be sure and mention, so that those would really stand out to you. Is a simple machine. So it says I'm supposed to say why it's a simple machine, because it allows me to use less force to do work. Okay. The mechanical advantage is the length of IP, that stands for inclined plane. The length of the inclined plane divided by the height of the inclined plane. So this would be 5 divided by 1. Okay, in our example we did here in the book with the truck. So that mechanical advantage would be 5. Okay. All right. With an inclined plane, as the distance gets longer, less input force is needed. The size of the input force is decreased. Okay, some of those keywords they want in the directions on this paper. Okay. The output force is the weight of the objects if it's just lifted. Okay. And the direction of the force does not impact an inclined plane. Okay, you're going in the same direction, so that's not really an issue here. Sometimes it is. We'll talk some more about those. Examples: a moving truck, a wheelchair ramp. I guess I should put a moving truck ramp. It's not really the moving truck. A wheelchair ramp and a slide are all examples of an inclined plane. Okay, so that's kind of what you'll be doing on that chart. Okay, for each of the 6. We just did one together, so if you freeze this, you can just type away, do a split screen, and copy that. That's fine. I wanted to do that one together with you. All right? Okay, let's keep going here. So here's a wedge, inclined plane that moves, so it's very similar to an inclined plane. A knife, axe, doorstop are all wedges. Okay, and I tried to add a few little things down here. I really didn't have a lot of room. They kind of left you hanging a little bit with some of these details, so I added some of that in. So the mechanical advantage of a wedge increases as it becomes longer and thinner. So a wedge can increase the distance. The more you increase the distance, the longer and thinner it is, the more of a mechanical advantage you have. Okay, so a longer, thinner knife is going to be easier to chop with than a short, stumpy one. Okay. But it also changes the direction of the force. And what I put here is hard to see: downward to outward. Okay, if you look at this knife, it's moving down. Okay, as she's chopping her veggies here, it's moving down. But what happens then is that downward force is changed to an outward force because the veggies are separating, they're splitting and moving apart. Okay, so you have that. I drew some arrows here. Downward force changing to an outward force. So that is also changing. The distance is possible to change with a wedge, but the direction also changes. Okay. I talk a little bit about wedges in the human body. That's great. Teeth, fascinating stuff. We love our teeth. Okay. Screw. Another form of an inclined plane is a screw. A screw is an inclined plane wrapped around a cylinder or post. Okay, I brought you a little example. So here's my inclined plane. Okay, I highlighted this side pink. Okay. And then I'm going to use this pen as my post. They talk about an inclined plane wrapped around a cylinder or a post. If I wrap it up, you can see what I get. Okay, or all these look at the highlighted, the colored line there. Those are the threads of my screw. Okay. Now, if I would make this inclined plane longer and skinnier, what would happen? I would get more threads and they would be closer together. Okay, so that's a really important idea with this concept of a screw. Just like a wedge changes the direction of the effort force, we talked about that right over here. A screw also changes the direction of the applied force. Okay, so that's a key, that it changes the direction. Also, the mechanical advantage of the screw is the length of the inclined plane. So the length of my inclined plane wrapped around the screw divided by the length of the screw. Okay, the screw itself, how long my post is. Okay. The more tightly wrapped the threads are, the easier it is to turn the screw. That would be increasing the distance. So the longer I would make this inclined plane, the more threads I would have on my screw, and increasing that distance is going to make it easier to turn the screw. Okay? All right, levers. Okay, levers. Here's some pictures of levers. The mechanical advantage increases as the fulcrum is moved closer to the output force. Okay, so this one, look at these two levers. Okay, we just said this. If the fulcrum, that's this guy, is moved closer to the output force, look at my mechanical advantage, it's 5. But if the fulcrum's way over here by the input force, my mechanical advantage is only 1/5. Okay, so I'm going to get a lot more work out of my lever if I move that fulcrum way down by the output force. This is you pushing on it. This is the lever pushing up on whatever you're trying to lift. Okay, all right. So it changes the direction of the force because you're pushing down and something else is going up. Okay, so it changes the direction of your force, and the input and the output force is related to the distance. It's related to the distance, how far this fulcrum is from my output force. That's the distance part. Okay. This is your seesaw, okay? That's what a lever is. And like I said, this is the fulcrum. The mechanical advantage of a lever is found by dividing the distance from the fulcrum to the input force by the distance from the fulcrum to the output force, okay? Which is why you can see here it was 50 input force to fulcrum divided by fulcrum to output force, 10, okay? Okay, there's 3 classes of levers. They're all pictured on this page. A lot of times we skip this page, but these are your first, second, and third class lever. Okay, and they give a nice explanation of that here. This you really only need to worry about if you remember from this page, okay, your Rube Goldberg assignment. It says right here, here we go, extra credit if you use more than one type of lever or pulley. Okay, so here's your 3 types of levers. I would really wait on that component when you build your Rube Goldbergs. See if you have time at the end. Building these Rube Goldbergs takes a lot more time than you think it's going to. And if you have some time at the end, keep that in mind for adding that extra credit component in. But don't worry about it right off the bat. Okay, but that is where they talk about it. All right, wheel and axle. 2 circular objects of different sizes that are attached in such a way as they rotate together. Think of a steering wheel. You have the steering wheel and the little rod that attaches to the center at the back, okay? So you have your wheel, and then the part that it attaches to is the axle in the middle, okay? The larger objects, the wheel, the smaller objects, the axle. The mechanical advantage is usually greater than 1. It's found by dividing the radius of the wheel. Remember, radius is half your distance. Remember, radius in the story, he was half the size of the mom. By the radius of the axle, okay? Wheel and axles change the direction of the force, okay? You're turning it around, right? This gives you a couple different kinds of wheel and axles and some examples up here. We don't really need to go into those. A pulley, here's our last one, is a grooved wheel with a rope or cable wrapped around it. Okay, pulleys also work by changing the direction of the force. A fixed pulley does not change the force you exert or the distance over which you exert it. Instead, it changes the direction. So the size of the force doesn't change, the distance doesn't change. It's just the direction of the force. It's easier to pull down with gravity than it is to lift up against gravity, okay? So just changing that distance is what makes a pulley a simple machine and makes the work use less force. Mechanical advantage of a fixed pulley is 1. And then over here they give you your 3 types of pulleys, a fixed pulley, a movable pulley, and a pulley system. Again, this also, the extra credit from the Rube Goldberg was if you could use more than one type of pulley. I have some pulleys I will let you use for your Rube Goldbergs. Again, I would not worry about the extra credit part, just worry about using one pulley for now. Okay. Movable pulley, the mechanical advantage is 2, and a pulley system, the mechanical advantage is 3. So mechanical advantage of 1, 2, and 3. That about sums it up. One more thing I wanted to add, okay? Tomorrow, okay, so that's what you're going to be doing today, is working on this chart. This chart is going to be due, and this assignment is due Monday, okay? So you have over the weekend and stuff to work on that. What you're going to be doing tomorrow in science is a couple things. Tomorrow in science, you're going to work on this assignment 4. You're going to list the items you brought, because remember, all supplies are due tomorrow, and do your initial sketch, okay? You can do this on the back if you need to, Make sure everything's labeled, okay? So I can tell what the parts are. This is just your starting point. You can change this as you go, and you most likely will. I've never had a group that's actually followed their initial sketch to the very end, but you at least need a starting point, okay? You're going to write your step-by-step description. Okay, remember you need at least 10 energy transfers, so 10 steps, okay? These are in your packet, okay? Assignment 4. Also, while you're doing that tomorrow with your groups, you're going to want to have this out to remind you of the specifics, what you're doing, the details of the assignment. So have this out also to be looking at while you're working on this tomorrow. Okay, my goal is for you to get this done tomorrow in class and resource room time. If you can't, you're going to need to try to work on it if you can over the weekend, maybe Monday morning before you start class, because we need to start building on Monday. Like Monday, we're going to come into my room and I'm going to have all the tables in there, and we got to get started because we only really have next week. Okay, so make sure you're thinking about that. I want to talk about it a little bit so you can come in tomorrow for science and really be ready to go on that. Okay, all right. I miss you guys, and I will see you on Monday. Bye.